Alright, it is now time to prove that Quicksort works. So we've talked about how it works. I've shown you an implementation in pseudocode of Quicksort. Now we're going to prove it. And we're going to do this partially by loop invariant, which is your exercise for this set of slides, and also partially by proof by induction on the recursive part of the algorithm. Alright, so before we do that, I just want to remind you in this set of slides how Quicksort actually operates. So if we're given an array, we're going to pick out an element and we're going to call it the pivot. For ease of discussion, I'm just going to say it's the first element. But again, we could just pick any element and sort of swap it into that first spot, and it would still work the same. It might have a little bit different running time characteristics depending on the properties of the array itself, whether it's in ascending order, descending order, or already randomized. So we partition around that element, which is going to put the 11 and the 13 to the left and all the other numbers to the right. And I do want to say that I did this by hand, so I didn't necessarily make sure that everything was sort of in its correct spot with respect to like how the actual code is implemented. So if this doesn't match exactly what you get with your code, if you were to put this in there, that's not a problem. It's logically correct in that everything to the left is in the less than partition and everything to the right is in the greater than partition. Alright, well, after we've partitioned, we then have our recursive calls. So our recursive calls are going to work on these two subarrays respectively. So, and again, it does this in place. We're not copying anything around, we're just passing the full array around every single step. So our leftmost array is this one. We're going to select the 11 as the pivot, and we'll pivot around that. It doesn't change, it doesn't move anything around. And there's nothing to the left of the 11, nothing in this space, so we hit our base case of one or fewer elements. Or the left index plus 1 is greater than or equal to the right index, so there's nothing to do there. On the right side, we also hit a base case in that there's nothing to do when you just have a single element. There's no reason to do any sort of swaps, you don't have to do any sort of call to partition. And again, left index plus 1 will be greater than or equal to right index in this case as well. So we're done with this entire left call chain. So now we come up to the top and we have this array that we need to partition and call recursively on. So we'll call 51 the pivot element, the 47 goes to the left, and the other three numbers go to the right. We have our left call, which is another base case because there's just a single element, and we have all the elements to the right. We'll partition around 91, which is going to give us this as the partitioned elements. And to our left, we're going to have 67 and 89. We'll pick 67 as the pivot. And there's nothing to the left, so that's a base case with nothing. Just a single element to the right. And then we come back up to here, nothing to the right, so we hit a base case. And that's our entire now sorted array. Let me remove my face from the screen. So how did every single element get into its correct sorted spot? They either did it by getting put there by sort of denoting it by a base case here, or by at some point being selected as the pivot. So the 11 was selected as a pivot, the 23 was a base case, the 31 was selected as a pivot, 47 base case, pivot, pivot, base case, and base case. So everything gets put into its correct spot in one of those two ways. Okay, so in our partition proof, we're going to start by proving the correctness of partition. For our quicksort proof, we're going to start by proving the correctness of partition. And just to make this a little easier, let me highlight the part that we care about. So this is the current subarray we're looking at. Or really, the current subarray we're looking at doesn't include that rightmost index, because we're always looping up to but not including the rightmost index. So how do we prove that partition is correct? In the past, what have we used when we were proving the correctness of something that's essentially just a loop? Well, we're going to do a proof by loop invariant. So again, we start by stating the loop invariant. So that's a statement that can easily be proven true or false. It should reference the purpose of the loop, and it should reference any variables that change each iteration. And we're going to show that the loop invariant is true before the loop starts. That's initialization. And we're going to look at the maintenance and termination criteria, the maintenance and termination conditions as well. So again, how does your loop invariant start usually? It's usually something like at the start of each iteration with an index, and then you reference something about the subarray. So what I want you to do is write a loop invariant, actually go through an entire proof by loop invariant for the partition procedure. And after you've done so, in the next video, I'll step you through my process where I show you my loop invariant and proofs for initialization, maintenance, and termination. My recommendation would be to come up with your own loop invariant, go through the process, and then again, if your loop invariant's much different than mine, as you'll see in the next video, pause my next video after I show you my loop invariant and see if you can go through the initialization, maintenance, and termination conditions with my loop invariant and see how closely you match what I show you.